In this video we're going to look at some other applications of integration by parts, most notably how do we use the fundamental theorem of calculus with the integration by parts, and another method known as the tabular method or chart method of integration by parts. So let's take a look at these. Let's say that we have the integral of 0 to 1 of arc sine of x dx. Arc sine is not a basic integral, it's not a u-sub, so let's try integration by parts. Notice that, like in the last video, arc sine is an inverse tangent and dx is algebraic. So I'm going to set up our u du, so u du, and then we have dx is going to be dv, so dv and v. Plug stuff in. U is arc sine x, so therefore du is 1 over square root 1 minus x squared dx. dv is dx, and so when we integrate dx we're going to get x. Therefore I can use the shape, and we're going to get that this integral equals uv minus v, the integral of v du. So we'll have x times arc sine x minus the integral of x divided by the square root of 1 minus x squared dx. And oftentimes that happens with the arc sine stuff, is that we have to do a u substitution. Now, notice that we do have limits on our integral. So here's how we deal with that. We deal with it the exact same that we did before. This piece, we already evaluated the integral, and so really we're going to put parentheses around this and then put the limits 0 to 1. And we have another integral here, and so the limits will carry over to this integral as well. So when we do this, let's evaluate this one right away. We're going to have 1 times arc sine of 1, if I could write arc sine of 1 minus 0 times arc sine 0. So that's evaluating the FTC for the first piece, and then minus, now we do have to integrate this, so we're going to use the u sub because we have x squared on the bottom and x on top. U is 1 minus x squared, so du is negative 2x dx. So we're going to need to doctor with a negative 2, counterbalance with a negative 1/2. The negative 1/2 will make this a plus, so make sure that you keep track of all your negative signs. So really, down here, this plus will make this minus a plus. Now we can do this second integral here. So we're going to have the integral. Now, because it's a definite integral and I did a u substitution, I'm going to change the limits. So we'll have the integral, or we'll have, let's see, Alright, so we'll have plus 1/2 integral, again, changing the limits. 1 minus 0 squared is 1. And then 1 minus 1 squared is 0. So notice that the limits, they don't flip-flop, they become new limits. And then my integral becomes 1 over square root of u du. Let's keep going, and I'm going to simplify as we go along. The arc sine of 1 is pi over 2, because the sine of pi over 2 is 1. So we have pi over 2. This term goes to 0 because it's 0. And now, check it out, I'm going to flip-flop the limits back because it's kind of weird evaluating it that way. And so because I flip-flop the limits, this plus will become a minus again. And so I'll have minus the integral from 0 to 1, and then the 1 over root u is really u to the negative 1/2 dx. And when I integrate this, we have our pi over 2 minus, and then the integral of u to the negative 1/2 is going to be u to the positive 1/2, and then divided by 1/2 is the same as multiplying by 2, evaluated from 0 to 1. And thus we will get, let's see, if I plug in 1 into this, I'm going to get 2 times 1 to the 1/2. Right, sorry, I forgot this 1/2 that was out front of our integral. So there is a 1/2 out front. Okay, so this 1/2 and the 2 will cancel, and then we can just plug in the 1 into our integral, because plugging in 0 will give us 0. And so our answer will be pi over 2 from the original x arc sine of x term, and then a minus 1 from the integral of the v du. And so this is our final answer. This is an example of how to do integration by parts with the fundamental theorem. Basically, you plug in the limits at the first piece and at the second piece and evaluate them normally. The last method of integration by parts that we'll learn is called the integration by parts chart. And this is used for when you have to do integration by parts over and over again. And oftentimes these will look like this sort of function where you have like x cubed sine of 2x dx, integral of x cubed sine of 2x dx. Now, if we just had the integral of x times sine of 2x dx, we could think in our heads, well, this is going to be integration by parts because I have an algebraic and then a trig term. These are different functions, so we'll use Lyautey, etc., etc. And then because essentially this is my, so here's my algebraic function, here's my trig function. A comes before t in Lyautey, so my u is x cubed. And now the thought process here is I am going to take du and I'm going to get 3x squared. Well, then when I integrate the v du, I'm going to get x squared times some trig function, so I'm going to have to use integration by parts again. That's the idea behind this. Now, to make this a little bit more organized, we're going to use the integration by parts chart. Here's what it looks like. There are 3 columns. The first column is very simple. It's plus or minus. We start with plus, and then we alternate. Very simple. Don't get confused. The second column is u and the du's, and they're going to be sort of together as one column. And then similarly, we're going to have dv and v as the antiderivatives. And so here's how we start. We start by splitting up the integral into its 2 parts. We had the x squared, which is algebraic. Algebraic comes before trig, so that's our u. And then the sine of 2x was our trig part, as you remember from here. And then all we do, or actually it was x cubed, sorry, x cubed here. And then all we do is we take derivatives going down on the u du chart. So x cubed, 3x squared, 6x to the 0, 6, and then 0. Where do we stop? We stop when we get to the first 0. Done. On the other side, we're going to integrate these. So the integral of sine of 2x is negative cosine of 2x, but there's a mini u substitution here, and so you get a 1/2 coming out. You can think reverse chain rule, etc., etc. Do it again. We're going to get negative 1/4 of sine of 2x. Do it again. We're going to get positive 1/8 cosine. Again, I'm taking the integral. And one more time, negative, wait, hold on. What's the integral of cosine? Positive sine. So we're going to get positive 1/16 sine of 2x. Okay? So you go until you get 0 as your derivative. So here. So really, this is going to line up like that. Those are all in the same row. And now what we do is we use a variation of the shape, and instead of going like this, we're going to go basically straight across and then down. Straight across, down, across, down, across, down, and then across. And so we should have, in this case, we'll have 4 things. And so the answer is very simple, because you just read it straight across. Positive x cubed times negative 1/2 cosine 2x. That's the first term. Done. Then we're going to have minus a negative, so plus 3x squared divided by 4 sine 2x. You kind of get the idea that we're just reading straight across. It's very simple. We're going to have 6x over 8, so I'm going to simplify that to 3x over 4, and then cosine 2x. Running out of space, let's see. The next term will be a minus and a plus, so it'll be minus 6 over 16. I'll just leave it as that. Make it easy. 6 over 16 sine 2x, and then plus 0. But then remember that this is an indefinite integral, and so we need our plus c at the end, and that is, oh my gosh, the answer. So the tabular method saves us from doing integration by parts over and over and over, because guess what? It does integration by parts over and over and over in a much easier to follow method. So hopefully this makes sense. Enjoy it. Yeah, it's pretty fun. Bye.